Algebra 2 skills number 37, exponential models. Let's take a look. The template we have here looks like this, where a, the number up front, is our initial value. That's what we start with. And what's going to happen is we're going to multiply the a times this 1, and nothing's going to happen. But if we add to or subtract from 1, a will change based on whether you add or subtract. So r is your rate of change. It could be going up or down. You can't do both. We have to pick here. We do want to make sure that's a decimal. We'll see that in our examples. T is just some sense of time. So remember, exponential means there's a variable in the exponent. So we're studying what happens if you take an initial value, you multiply it by some value here that's going to change from 1 based on an r, and we're going to multiply over and over to a, and we're going to allow that variable to change to kind of observe what happens. For our first example, we have a town here that has a population of 5,000 and grows at a rate of 6% per year. So again, we have this template. Our initial amount here is 5,000. And notice here we are adding. You can't do both. You have to make a choice based on the context of the problem. And you're growing here, so you're going to add 6%. That's 0.06. Okay? Because remember, 6% literally means 6 divided by 100. Okay, which is easy to do without a calculator. You're just going to take your decimal and move 2 positions to the left. So a very common mistake here would be to leave the 6, and it's easy to identify that error because you can get a huge number if you make that mistake. But it is 0.06. And for now, we're going to let t be t and just observe what happens as it is allowed to change. Now notice that this value here, this is called a growth factor, is bigger than 1. Therefore, you're going to grow. Specifically, how many people will there be in 5 years? We're going to take that model and simply insert a 5 in where t is, and you get 6,691. That makes sense. So you're growing by kind of a small percentage, but you are growing, so it should be bigger than 5,000. Also, in context here, we're talking about people, so you want to round to the nearest person. The second example, a truck is worth $40,000 and depreciates. That means it goes down in value at 8.7% per year. So there's our model. And again, we're going to put 40,000, our initial amount. This time we're depreciating or losing value. Remember to move your decimal 2 positions to the left. Okay, and that makes a growth model here, or excuse me, a decay model, not a growth model, a decay model. And you can tell that because the number here is less than 1. Okay, so specifically, how much will the truck be worth in 6 years? All right, so we put a 6 in there, and you can see the values dropped quite a bit. And this is money, so in context, we round to the nearest cent. Okay, here's a table from example 2. A lot of times you'll use, now this is from Desmos, but you can get on a calculator. And I type the model in, and you can see at 0 years, or at first, it's worth 40,000. But as time goes by, the truck loses value. So sometimes a table is very helpful in this section. A third example, sometimes it's not a percentage. You're just told that it doubles or maybe triples, or you're cut by half or something. But here it says the amount of views for a viral video is doubling every hour. Okay, if 180 views took place for a particular hour, write a model for the number of views t hours after the initial amount. So I point this out. There's your model again. We're not actually going to use an r. Technically, if you're doubling, you're adding 100%. But doubling in context, that just means your growth factor here is 2. Okay, so you don't really think about r right here. You just take doubling and you make a 2 there. So I wanted to point that out for your exponential model.